All right, we have. I think we should have enough people by now. And let me also turn my own recording. All right, good morning or good afternoon, everybody. Uh, let's begin our sixth lecture today. Can you guys all see my shared screen with my notes?
Yes, I can see you. Okay.
Great, thanks. So today I wanted to gently transition into doing some homotopy theory via sheaves of groupoids and infinity groupoids. And again, our motivating example is to understand how differential geometric objects such as vector bundles can be understood as local structures in the sense of sheaves. So let me first briefly recall what a vector bundle is. And the definition I chose to review here may not be phrased in the most familiar way, but in fact it's pretty much exactly the same as what you may have encountered in your traditional differential geometry class. So let's say B is a smooth manifold, and I'm going to consider a category of submersions over B. Its objects will be a smooth manifold, capital T, called the total space, which maps to B via a submersion. And let's recall that submersion simply means the tangent map on tangents is surjective on tangent spaces. And a good way to think about a submersion is that a submersion is basically a way to formalize the idea of a smooth family. In this case, the smooth family will be indexed by the smooth manifold B, a smooth family of smooth manifolds. Maybe I can even write it down. So that's basically a B indexed smooth family of smooth manifolds. Oops. And morphisms will be simply commutative triangles. All right, so in this category, we can construct rings and modules using the usual definition, but replacing sets everywhere with objects in this category, submersions over B. In particular, we can construct real numbers as an object in this category. So that's, I guess I wrote it down a bit below. Over every point of B, you have a copy of real numbers. And before maybe I talk what a ring object is, let me point out that in this category of submersions over B, colimits and connected limits, at least those colimits and connected limits that exist, these are computed at the level of total spaces. So what this means is that you have a diagram of objects in the category of submersions over B, and you want to compute this colimit. Well, what you do is you simply compute the colimit of total spaces, and then the colimit canonically maps into B. using the universal property of colimits. And likewise for limits, not all limits, but connected limits, meaning limits whose indexing diagram is connected. So any two objects can be connected by a zigzag of morphisms going in any direction. And the only other type of a limit or colimit we haven't considered yet is products. And products are a bit different in the sense that the products will not be computed at the level of total spaces, but rather products will be fiber products over B. And the wonderful fact about the submersion, by the way, is that, in fact, it's in a sense a defining property even that submersions have a have pullbacks. So a defining property of a submersion is that if you have a diagram, a commutative square. So let's say you have an arbitrary smooth map of base spaces. Then the pullback of this diagram exists and can be computed as the usual fiber product. So this pullback always exists if this map here from T to B is a submersion. So that's as far as I think, yes. So it's pretty much an if and only if statement. So if you do have such a map and you do know that arbitrary base changes exist, then you can show it is a submersion. All right. So basically, almost all limits and colimits are computed at the level of total spaces, with the exception of products. So products are computed as fiber products. Which means, in particular, since we do have finite products in this category, we can talk about algebras over algebraic series, like rings or modules. Both of these make sense now because both rings and modules are defined using diagrams with finite products. So you can make sense out of these diagrams in this category of submersions over B. Okay. Any questions so far before we transition to explaining how vector bundles are modules? All right, so yeah, so here I gave an example of real numbers. So as I mentioned before, you think of an object in submersions over B as a B-indexed family of smooth manifolds. In our case, the smooth manifolds will be a copy of the real line itself. And you do have the operations of addition, multiplication, and so on in this ring object. For example, both addition and multiplication will have as its domain the fiber product of R times B and R times B again over B. And that means this fiber product can be computed as the ordinary product of R, R, and a single copy of B. And over every point of B, you simply see the usual addition or multiplication operation. So you think of this ring object as a over every point of B, you have a copy of the usual ring of real commutative ring of real numbers equipped with its smooth structure. And then a vector bundle will be a module object over this ring object. So this means over every point of B, I have a smooth manifold, and this smooth manifold is equipped with the structure of a module over real numbers. In other words, over every point of B, I have a real vector space. And these real vector spaces, they vary in a smooth way as you move around capital B. So here, yeah, so that's how you think of a vector bundle. So I have a, maybe I should have drawn a picture somewhere where I still had space. Yeah, so here is a, it's difficult to squeeze in. Oops. Maybe I can squeeze again here. So here is B. And here is a picture of T. Oops. So the individual fibers here are what lives over a certain point in capital B. And you also have in every fiber, you have a zero element, which I'm depicting here by this section. And you also have a structure of a vector space on every fiber. So you have the operations of addition, multiplication by a real number, and these operations are always given by certain smooth maps. Okay, so that's the traditional definition of the vector bundle. I could have probably talked a bit more about examples, but the most traditional example, of course, is the changing bundle, denoted by capital T, where the fiber over every point is tangent vectors at this point. And tangent vectors can be defined in a whole number of different ways using either the kinematic definition, where you say you have an equivalence class of smooth curves passing through your point, or you can use the algebraic definition, where you say I have a derivation at this point. So depending on your preference, you have a whole variety of ways to define the tangent bundle, for example. And the question, the sort of issue I would like to talk about this today is the notion of a vector bundle appears to be local in B. And we previously saw how entities that are local in B can be expressed as a map from B to a certain smooth set, or more precisely a sheaf on the side of Cartesian spaces. So any smooth manifold can be interpreted as a smooth set, as we saw previously in a few lectures ago. So B here is, strictly speaking, not the same B as before, but rather it's a pre-sheaf of sets obtained through the restricted Young-Aga embedding. And the question is, since so at every point of B, I have some local data like a vector space, and this data seems to vary smoothly. So perhaps it is possible to express a vector bundle as a map from B to a certain smooth set of vector spaces, which is supposed to classify vector spaces in smooth families. And this would be a very, very intuitive expression of the idea that a vector bundle assigns a vector space to every point of capital B, and this assignment is a smooth map in some sense. So, and I guess we could say perhaps that smooth maps from B to vect should be the collection of all vector bundles over B. But what exactly do I mean when I say a collection? There are in fact several options. You can either say the set of all such vector bundles, and this is slightly problematic because in the usual definition, vector bundles will form a proper class as opposed to an actual set, but this is not the main problem here. The actual problem with this definition is that it does not allow us to see that isomorphic vector spaces are in some sense the same. So this definition, if I just say it's a set of vector bundles over B, well, in the set it will have many isomorphic copies of the same object, which will all appear as completely different elements. So maybe I should even write this down. Isomorphic elements, isomorphic bundles, I guess, are different elements in this set. And this is problematic. Like when you study algebra, for example, one of the first things you do is you introduce the notion of an isomorphism of groups, or whatever algebraic structure you happen to be studying at the moment. And of course, that's a very good idea because otherwise you would have, for example, a proper class of groups with one element, right? You can take any set, place it inside of a singleton set, and equip it with a unique structure of a group. And these will all be different groups unless you introduce the notion of an isomorphism. So we certainly do want to somehow identify the isomorphic vector bundles. So you can say, well, okay, the most obvious solution is to simply say I have the set of isomorphism classes of vector bundles over B. That should certainly resolve the problem of isomorphic vector bundles being different elements in this set. Now they are the same element. But unfortunately, that's still not quite the correct solution. And the main problem now is that every vector bundle is locally trivial. Meaning, and I guess this is one aspect that was not totally clear from my definition above, but if you have a submersion and you know that it's equipped with a structure of a vector bundle, then you can fairly easily prove it is a locally trivial. So locally trivial means you can find for any vector bundle over B, I can cover B by some open subsets. And when restricted to the open subset, the vector bundle becomes isomorphic to the trivial vector bundle. So the trivial vector bundle simply means, and I don't have any space here either. Let me just as another example, well, generalizing what I said here about real numbers, you can slightly more generally say, if I consider the projection map from V times B to B, where V is a real vector space, this is called the trivial vector bundle. Probably should have given you an example of a non-trivial vector bundle. Well, you may be familiar with the Möbius strip, which sort of goes around a circle with a twist. That's an example of a non-trivial vector bundle. Yeah, so what's the problem with vector bundle being locally trivial? Well, if we do take the set of isomorphism classes in this definition, then remember how we talked about how a section of a smooth set can be restricted to an open cover, and the restriction to some open cover contains the same information as the original section. So here, if I restrict a vector bundle to an open cover where the vector bundle is locally trivial, so trivial on every element of the open cover, then all of a sudden I see that when passing to a sufficiently fine open cover, in fact, any good open cover will do. So let's recall that a good cover is an open cover where every element and every finite intersection is either empty or diffeomorphic to Rn. So over Rn, every vector bundle is trivial. And if you pick a good cover of your capital B over this good cover, over every element of this good cover, your vector bundle will be trivial. In other words, all vector bundles now look exactly the same. Exactly the same. Which means there is no hope for you to have this definition. It will not satisfy the sheaf property, right? Because you can see that different non-isomorphic vector bundles, when you restrict to a certain open cover, suddenly restrict to exactly the same sections over this open cover. So you all of a sudden cease to distinguish between non-isomorphic vector bundles. So the previous attempt did not work because we had too many copies of isomorphic vector bundles, and now we have too few copies because things that were not isomorphic all of a sudden appear to be isomorphic to us. So both of these approaches do not work. And what was the problematic ingredient here? The problematic ingredient here was that we are insisting that vector bundles form a set of some kind. And as we know, maybe from algebra, right, you typically do not talk about the set of all groups, but rather you will talk about the category of all groups, or maybe the groupoid of all groups. And of course, the same ideology continues to apply for vector bundles. And so maybe smooth maps from B to vector should not form a set. Perhaps they should form a category or a groupoid of vector bundles. And as it turns out, that's the correct approach, and it does lead to correct and interesting answers. But it also means that our previous formalism of smooth sets is simply not sufficient anymore. And what we really need is a smooth groupoid or a smooth category. Smooth category, or maybe a smooth groupoid. A smooth groupoid is also called a step in a different settings of algebraic geometry, as is smooth category sometimes. Okay, so what is a smooth category? Let me scroll here. By the way, just to remind you, we have a website which has video recordings for all talks and also handwritten notes. And I think, yeah, I did upload today's notes also, so they are available online. All right. Yeah, any questions so far?
Can you repeat in short why we choose smooth map as a category and why we um, um, don't accept other things?
Yeah, so the reason we don't want to accept the first two solutions is like in the first case, isomorphic vector bundles would appear as different elements in this set, and there would be no way to see they should actually be considered as the same. So you would have all of a sudden a huge number of isomorphic copies of the same object, and there's no way to distinguish between them. So there are different elements in this set, even though they should in some sense be considered the same. And the second solution does not work because it identifies too much. Any two vector bundles over B will locally look the same in a sense that over B we can pick a good cover, and when we restrict to elements of this good cover, any two vector bundles will become isomorphic because they will be trivial. Well, if they have the same dimension, they will be isomorphic. Otherwise, the dimension will be the only remaining invariant. So it doesn't work because we identify too much. Things that should not have been identified are now the same. So the only invariant you see from a vector bundle now is dimension, which is not enough. Like you really do want to be able to see non-isomorphic vector bundles. So both solutions do not work because they either don't identify enough or identify too much. And the last solution makes sense because it captures everything there is to know about vector bundles, the whole category, or maybe the whole groupoid of vector bundles. So clearly in the last solution, if we can somehow make sense out of it, we can all the information we want is captured here. So this category or groupoid knows how to identify isomorphic vector bundles, but on the other hand, it's not going to identify too much. Like here, we took isomorphism classes. Well, in this category, you don't take isomorphism classes. You keep isomorphic objects different, and an object can have a non-trivial group of automorphisms. And this group of automorphisms is not recorded in the first two solutions. So maybe one thing I should point out is that the last solution, I really don't have any space to write here, but the last solution knows about the group of automorphisms of any object, any vector bundle over B. So this group of automorphisms is impossible to see in the first two approaches. And as it turns out, it is really crucial to making sense and crucial to developing the whole theory.
It's a key
All right.
moment, yes, the group of automorphism. Yes.
Say again, sorry.
Yeah, it is a key moment, yes, about group of automorphisms, which we can't capture in the first two solutions.
Well, yeah, in algebraic geometry, it would be no longer this name, but here it's we are doing differential geometry. You would just call it the group of automorphisms. That's all. Yeah, but notice also that here the morphisms of vector bundles are inducing identity map on the base space.
Thank you.
All right. So let's see now what exactly is a smooth. Let's see. Keep it here. What exactly is a smooth category? And our definition is going to be pretty much a replica of the definition of a smooth set. As before, we are going to have a contravariant functor from Cartesian spaces and smooth maps. True. And previously here we had the category of sets. And now I'm going to place here the category of small categories and functors. Or alternatively, you could have chosen small groupoids and functors. And presumably, as before, we should have some kind of a gluing condition. And let me not repeat the most general possible gluing condition. Let me maybe sketch just the simplest possible version, where you have the union of two open subsets, U and V, of some Cartesian space. So their union is a Cartesian space. Then maps from U union V into F should be the same as a map of U into F and a map of V into F. And these two maps are supposed to be compatible on the intersection. So as before, we can try to write down a complete analog of the definition for sets. We can write down the same diagram, the same fork, where you restrict from U union V to U and to V. And then you restrict from U and from V to the intersection. And you have two different maps depending on which component you restrict. But this definition, as it turns out, will not quite be correct, because equalizer forks will have to be replaced with something called a homotopy equalizer fork. But let me, before we try to go into the details of the gluing condition for smooth categories, let me instead try to give you an example. So I'm going to try to construct a vect as a smooth category. So this means that given a Cartesian space S, I have to construct a vect S. And vect S should be a category. It should be presumably giving our description here. Smooth maps from B to vect should be the category or the groupoid or vector bundles over B, I should have said. So in particular, when B is a Cartesian space, smooth maps from a Cartesian space to vect by the Yoneda lemma should be the same as the value of vect at S. And this value should be the category of vector bundles over S. Now, over a Cartesian space, any vector bundle is trivial. It's isomorphic to the trivial vector bundle with some fiber. So one advantage of this approach with sheaves on Cartesian spaces is that many differential and topological objects tend to simplify considerably over Cartesian spaces. And that's exactly what we see here, that over an arbitrary smooth manifold, of course, you would have non-trivial vector bundles. But over Cartesian spaces, all vector bundles are trivial. And we exploit this nice fact by simplifying the description of our category. So instead of recording the whole gauge of a vector bundle over S, since we said that all vector bundles are in fact isomorphic to trivial bundles, so meaning projection maps from V times B to B, I'm going to only record the gauge of V, since everything else can be, V is a vector space, and everything else can be reconstructed from V. So objects in my category of vector S will have as objects the gauge of a vector space V, which you should think of as the encoding the trivial bundle over capital B with a fiber capital V. Notice that, of course, morphisms in this category are not going to be just linear maps between vector spaces, but rather they will be morphisms between the corresponding trivial vector bundles. So I have a trivial vector bundle V1 times B over B, and V2 times B over B. And I have a morphism between them, which is a smooth map from one product to another that makes this diagram commutes and preserves all the operations, all the algebraic operations given to us. Which means that over every point of capital B, I have a linear map from V1 to V2 And these maps from V1 to V2, they vary smoothly. I guess at this point we are already talking about S, so maybe I should have said S. Sorry about that. Oops, too much. So over every point of S, I have a smooth map from S to the vector space of linear maps from V1 to V2. So this home simply is a vector space of linear maps from V1 to V2. So these are the morphisms in my category. So this completes the definition of vector S as a category. But let's not forget that to specify vector as an object in smooth categories, I also have to tell you what happens when I have a morphism of Cartesian spaces, so some morphism H. I must specify for you the corresponding functor between the categories of vector bundles over the codomain of H and the category of vector bundles over the domain of H. So this is what we can call the value of vector on H. And this functor is very easy to describe. It's simply the pullback functor, right? If you have a, I really somehow ran out of space. Let me spill over to the next page. If you have a vector bundle over some arbitrary base B, and if you have a smooth map, you can pull back. And previously we saw this works with submersions, but of course, if the fibers of this map from T to B are equipped with a structure of a vector space, then this structure will survive in the pullback. So vector bundles can be pulled back. And this is exactly what happened here, but so this is a description of the functor. I send a vector space V to itself, which corresponds to the fact that if I pull back a trivial vector bundle, then a trivial vector bundle gets pulled back to the trivial vector bundle with the same fiber. So in this category, capital V represents the trivial vector bundle with a fiber capital V. And this trivial vector bundle gets pulled back to the trivial vector bundle. And a morphism F, so this I guess was called F here. A smooth map from S to linear maps from V1 to V2. Well, if I have a map from S2 to this home, and I also have a smooth map from S1 to S2, I can compose F and H. And this is how my pullback works on morphisms. So this completes the definition of vector as a smooth category. So as a contravariant functor from Cartesian spaces to categories. Any questions so far? All right, let me sort of move on to pointing out that this definition that what we gave so far has multiple defects. And probably the most serious defect is that it doesn't give us what we want. Recall that our original motivation was to ensure that smooth maps from B to vector are the same as a category or maybe as a groupoid of vector bundles over B. And unfortunately, this property fails more or less catastrophically in our current description, because if I compute the category or the groupoid of smooth maps from V to vector, this will be the category of trivial vector bundles over M. And maybe I should have mentioned maybe a few more details. Why is that the case? Let me in fact insert some lines here, and I will maybe add a few more details. Oops. How do I insert maybe a whole page? Yeah, let me just insert new page. Oops. Let's compute I should give you at least one complication. Where M is a smooth manifold. Well, let's recall how a smooth manifold is a smooth set, right? So here we sort of implicitly embed smooth manifolds into smooth sets, which are contravariant functors from Cartesian spaces to sets. And under this embedding, M corresponds to the functor that sends S, a Cartesian space, to the set of smooth maps from S to M. That's how a smooth manifold is turned into a smooth set. Okay, so now let's look more closely at morphisms from M to S. M to vector. Well, morphism of presheaves is a natural transformation. So here, maybe I should say, I have the category of Cartesian spaces opposite. I have my M, which lands in space in sets. And I also have vector, which lands in small categories or maybe small groupoids. And of course, sets and categories are different categories, so you cannot consider natural transformations between functors landing in different categories So what has to happen here is we must promote a set to a discrete category. So there is an embedding of sets into categories that takes a set and converts it to a category where the only morphisms are identity morphisms. All morphisms are identities. And the set of objects will be precisely the given set. So this is known as a discrete category. So, and once we promoted M to a pre-sheaf of categories, in other words, a smooth category, we can talk about natural transformations. What is such a natural transformation? What's called T for transformation. What is T concretely? Well, a natural transformation assigns to every Cartesian space, every object in the domain here, we assign Ts, its component, which will be a functor from ms to vector s. And let's recall that this category here only has identity morphisms. So to specify a functor out of a discrete category, I only have to tell you what happens to objects. And objects in this category are smooth maps from S to M. Say a map F from S to M, which is a smooth map. That's an object in this category, in this discrete category. And such an object must map to some vectors, to some object of vector S, was recorded in vector S.
Please, can you
Vector
repeat
S.
about the second row in the diagram above?
What's the question?
Please, can you review in more details the second row in this diagram?
The second row, you mean the bottom
discrete
arrow?
category about.
This one?
Yes, about this, yes, about the second row, yes, about this row, yeah, from set to cat.
Okay, yeah, this inclusion, yes. So that's a discrete category functor. It sends a, what we call it, X, a set. It sends it to a category called disk X. That's a category. Its objects are the same as the set X. And the only morphisms in this category will be identities. So if the only morphisms will be identities on elements of X. And because all morphisms are identities, there is no need for me to specify composition, the operation of composition, because composing or sourcing target, because we know how to compose identities, and we know how to compute the sourcing target of an identity morphism. And since there are no other morphisms in our category, there is nothing else to specify. So all the other giga.
Now, what is the main motivation for our consideration in our case of this aspect?
Well, the only motivation here is that we want to convert sets to categories because we want to make capital M and vect objects to be objects of the same type. Previously, one was a pre-sheaf of sets, and the other one is a pre-sheaf of categories, or groupoids, if you want. And how to include sets into categories? Well, that's the most natural. This inclusion is the most natural possible inclusion. So the point is that if you have a discrete category, it contains the same data as its set of objects. There are no non-identity morphisms between them, so in a sense, a discrete category behaves precisely like a set. So this functor GISC is a fully faithful functor. Maybe I should have mentioned this. So fully faithful. Meaning morphisms between true sets are in a bijective correspondence with morphisms between the corresponding discrete categories.
I'm trying to figure out how this is linked to M, which belongs to category of manifolds.
Oh, you mean what happens when we compose M with this functor?
Yes. I'm trying to figure out how they to join and follow one.
Yeah, so that's what I tried to mention here. So when we compose, I should have probably said GISC here also. Let me actually be a bit more precise. So let me spell it a bit more carefully. So this is actually GISC M evaluated at S. So this trig M composed with a discrete functor and then evaluated at S. So this will be, this here is a discrete category on the set. The set of objects is precisely the set of smooth maps. So objects in this category are precisely the smooth maps from S to M. For every smooth map, you have a single object. The only morphisms between such objects are identity maps. And so it's a huge category. It has uncountably many objects, and that's perfectly fine. That's not a cause for concern.
Thank you.
All right. So this functor Ts provided to us by a natural transformation T should send such an object from S, a smooth map from S to M. It should send it to an object. So the set of objects here should map to the set of objects of vect S. And here the set of objects is a set of vector spaces. Oops. Somehow I'm not sure why it constantly moves up and down. So this gauge of Ts assigns to every smooth map F from S to M a vector space, which in principle could be a its own separate vector space for every f. So let me call it maybe V. So f maps to some vector space Vf, which in principle, theoretically, could be a separate vector space for every f. But as it turns out, that's not actually the case. All these vector spaces are exactly the same. And how can we see this? Well, we can see using the condition of naturality.
Is the truth for any f? Yes. Which kind of conditions we need to apply for f for obtaining vector spaces?
Yeah, so the natural transformation sends an object in this category to a vector space. An object is just a smooth map f from S to M. Such an object f is mapped to some vector space Vf. And a priori, all these vector spaces can be different. And as we will discover in a moment, the naturality condition forces all of them to be the same, which will ultimately prove that the what you get here is precisely the category of trivial vector bundles, because this common vector space will be precisely the vector space which is the typical fiber of your vector, it is the fiber of your trivial vector bundle. So let's see how the naturality condition forces all of those potentially different vector spaces to coincide. So let's pick a map from S1 to S2. Not sure why I'm still writing in green. You have a map from S1 to S2. Let's call it H as before. And H induces a naturality square. And in particular, the top map sends F, which we discover here on the right side is a smooth map from S to M to the composition of F and H. Whereas the vertical natural transformations, TS2 sends F to VF2, and here I'm a big, okay, VF2, and F composed with H is mapped to VF, YF2, there is no F2, there is just F. Like this. And finally, the bottom map is the pullback map. The pullback map for trivial vector bundles. And previously we saw how it works, right? Pullbacks of trivial vector bundles are again trivial. And we saw precisely here on the left side, we defined this functor from vect S2 to vect S1 as the pullback functor. And we saw that if you pull back a trivial vector bundle with a fiber V, you again get a trivial vector bundle with the fiber V. So the bottom map, the bottom functor, sends VF to itself. And the commutativity of the diagram means these two vector spaces must coincide. So even though a priori the notion of a natural transformation could have provided us with a whole bunch of different vector spaces, we now see that a lot of them must coincide. Specifically, the vector space assigned to some map F from S to M must necessarily coincide with the vector space assigned to the map given by precomposing F with any map H. Now, if you contemplate this for a moment, what do such equalities force on you? And you will see that they basically are forcing you all of those vector spaces to be the same, because you can connect any map F to any other map F using a chain of such equivalence relations as here. And to be more precise, let's say I'm given some F, a smooth map from S to M, and I'm given some G, a smooth map from T to M. And as long as M is connected, let's assume for a moment that yeah, I think M has to be connected, but that's not a serious restriction. Connected. As long as capital M is connected, it is possible to construct H. Well, let's see. So let me say, for example, let's map some arbitrary point R0 into S. And let's map R0 into T. And then I can map both to R1 like this. So any 2 points in M can be connected by a smooth path, and this smooth path is a smooth map from R1 into M. So what is happening here? So I start with 2 arbitrary maps, F and G. F is a smooth map from a Cartesian space S to capital M, and G is a Cartesian map from T to capital M. Then I pick some totally arbitrary map from R0 into S and R0 into T, and I compose F and G with these 2 maps. So according to this relation here, the vector space assigned to F here is the same as the vector space assigned to the composition from R0 to S to M. And likewise, the vector space assigned to G is the same as the vector space assigned to the composition R0 goes to T goes to M. But now so R0, the maps from R0 to M, both maps from R0 to M pick out some points in capital M. And if I assume capital M to be connected, any 2 points in capital M can be connected by a smooth path. So let's pick some arbitrary smooth path connecting these 2 points. And then we'll have a commutative diagram like this, where this is a smooth path. And these 2 maps will include R0, which is a point, into R1 as some points on this path. These points are connected in M. So this fairly simple diagram shows you that what does it show to you is that Vf is equal to Vg. Because F and G were connected, so Vf, let me call this P and Q, and the path, I guess I will have to call R. Yeah, so I'm running out of space, so maybe I should insert another page here.
T and S, what's about them? Please can you explain? In this case, about T and S, I understand that R0 and R1 is a point and path in our manifold, yes? And what's about S and T?
S and T are just arbitrary Cartesian spaces, so that's this S. So the point is that giving S and giving a smooth map from S to M, F I assign to such a Giga of F. So in particular, F contains capital S as its Giga. So I assign to such a Giga of S and F, I assign a vector space VF. And what this diagram is supposed to illustrate, if I can manage to maybe finish it properly. So here I will have U and V, and here I have R. So on this side, I can say VF equals VF composed with P, which is equal to V. So PF equals UR. So U composed with R, which is equal to VR. And VR, now we can go in reverse, is equal to VR composed with V, which is equal to VG composed with Q. Which is equal to Vg. So through this chain of 1, 2, 3, 6 equalities, we see that Vf equals Vg. So the takeaway from here is that we were computing maps. So let's not forget what our original intention was. We were computing maps T from capital M into the smooth category vector like we previously defined. And through this configuration here, through the simple computation, we discovered that such a natural transformation as a Giga, it contains a Giga of all VF, but all of these VF happen to be the same. So in reality, T yields a single vector space V. So a natural transformation from M to vect is the same data as a single vector space V, which you should think of it as a trivial, the trivial vector bundle V times M over M. So it seems like our definition is a failure. It doesn't give us any non-trivial vector bundles. Somehow we computed these natural transformations and we discovered that we only see the trivial vector bundles, and that's not good. We want to see all of them. So what exactly is the reason for this failure? And there are many explanations, but basically it looks like we failed to account for transition functions. So the problem with this computation is that there is no place or space for transition functions to be in. Right? So instead of saying here, instead of saying that Vf equals Vf composed with H, what we really want, if we recall the usual notion of a transition function, when you restrict to some, say H, for example, let's say H is an open inclusion, then composing with H amounts to restricting to a smaller open subset. And what we want instead of this equality, what we really want is an isomorphism. An isomorphism. Which would be encoding the corresponding transition function for a vector bundle. Unfortunately, that's not provided to us by the current formalism, which really was an obstacle for a while until Grothendieck suggested a solution in somewhere in 1960s, I guess, how to incorporate this. So and the solution basically is like you modify the notion of a map or natural transformation to allow for such isomorphisms. which gives rise to what is called stacks. Oops. And there are several sort of implementations of this solution. And maybe the most obvious implementation is to observe that categories or groupoids, they don't form a category. They form a true category. That's a different type of structure. So what you could have said, one possible option to proceed now is to develop a theory of sheaves or pre-sheaves valued in a true category instead of an ordinary category. And of course, the obvious problem with this approach is that when you study higher gauge fields, like the B field or the C field in supergravity, you will see not just groupoids, but higher groupoids. Instead of groupoids, you may see two groupoids or three groupoids. And then if you have chosen the solution with two categories, all of a sudden you now have exactly the same problem as before, repeated on a higher level. So instead of trying to endlessly chase through the whole hierarchy of n groupoids, we might as well say, let's go immediately to the last step, all the way to infinity. And this, when we go all the way to infinity, a miracle happens. A miracle happens in the sense that infinity groupoids, which we will discuss in more detail a bit later, they themselves form an infinity groupoid. So the theory can handle itself. There is no, like, previously it seemed like, oh yeah, we have to, in order to study sheaves of valued in categories, you inevitably need sheaves valued in two categories or two groupoids, then inevitably need n groupoids. But here the process stops. Sheaves of infinity groupoids themselves form an infinity groupoid or infinity category. Okay, we have some questions. Do I understand the commutativity of the square in a strict sense? Yeah, that's exactly that's exactly. So the question from Jack asks if we understand the commutativity of the square. Let's see which square we have. Yeah, that's exactly what I was mentioning, that yeah, either this square would have to be non-strict or only up to an isomorphism, and this would be accounted for precisely by the solution. So one way to interpret this solution is that it forces this square here to be commutative, not up to an equality, but only up to some isomorphism. And this isomorphism itself has to satisfy a coherence condition. And that's exactly what I want to talk about right now. Okay, so the formalism is sort of in order to avoid endlessly chasing through n groupoids for ever higher values of n, which some people gig for a while, I must say, which is a really strange thing to do, but you will see papers about sheaves of sets, then papers about sheaves of groupoids, then papers about sheaves of true groupoids. And I think already at that point it was clear that this is a path to nowhere, and you really should do infinity groupoids right away. And that's what we will be trying to do now, to try to understand maybe first what is an infinity groupoid, and secondly, how to work with infinity groupoids, and how to define smooth infinity groupoids, and how to work with them. And I think we are, okay, it's an hour and a half, so probably it's a good place to stop here, because then of course we would have to go into homotopy theory to define infinity groupoids. So, but probably it's best not to start a new topic right now. So in 90 minutes, I think is a very good time to stop. So I think that's it for today. And do you guys have any more questions?
As I understand, yes, groupoids are needed for constructing higher dimensional Gauss theories, dimensional gravity theories, yes, as I
Yeah,
understand.
for example, I mean, just to give you maybe some example, like B field. So maybe I should first say like electromagnetic field. Is an example. So that's just a principal you want bundle with connection. With connection. Or alternatively, is the same thing as a Hermitian line bundle with connection. So this would be an example that fits into what we discussed today. But of course, the electromagnetic field is not the only possible example. For example, I have a B field, which is a bundle gerb with connection. So that's what is called a higher bundle, or higher categorical bundle, or categorified line bundle, or whatever. But it gets worse. For example, in supergravity, you got something called a C field in supergravity, which is a bundle to gerb with connection. And bundle gerbs with connection form a, so principal U1 bundles form a groupoid. Bundle gerbs with connection form a true groupoid. Bundle two gerbs with connection form a three groupoid.
What about Young-Mills theory? Also, groupoid is appropriate for
In
Young.
Young-Mills, you have principal G bundles with connection. That's an ordinary groupoid.
Thank you.
And maybe one more example, just to think if nothing could be worse than a C field, Ramon fields. This is something called a co-cycle in differential K theory. And these very naturally form not an n groupoid for any finite value of n, but these are infinity groupoid. It's so maybe to motivate, we are going to infinity groupoids not for the sake of generality, like generality for the sake of generality, but rather it's a generality for the sake of encoding physically realistic objects such as Ramon fields in, well, okay, maybe saying it's physically realistic is a bit of a stretch, but it's a construction you need in theoretical physics. So this is was not invented by us. It's something that has been known since at least 1990s, and originally was not formulated in this language, but eventually was recognized that, yeah, Ramon fields should be just co-cycles in differential cases. And it's just unavoidable that these form an infinity groupoid. Yeah, so that serves as a bit of a motivation, I hope, for you. Yes?
What's about M theory, string theory? It's also
Yeah, M
described.
series string theory. I mean, Ramon fields, I guess you can say, is a part of string theory. So that would be one example. And of course, you do have other fields in string theory, so they also form various higher categorical structures. Yeah, but Ramon field, I would say, is a representative example.
It means that M theory is described by infinity groupoid, right?
Yeah, so like depends on what specific flavor of M theory you are talking about, but for example, you can like Urs Schreiber and Hisham Sati are developing something called hypothesis H, which basically says fields in M series should be presented as maps to a sphere, which also form an infinity groupoid. It's anyway, this is probably not a good time to talk about this in details, but there are plenty of examples of higher groupoids in many branches of physics. All right, more questions. Yeah, so next time I will have to talk about homotopy theory and what an infinity groupoid is, and how can we talk about sheaves of infinity groupoids. And this will fix the defects that we previously identified somewhere here, yes. Once we define an appropriate notion of a sheaf of groupoids, smooth maps from M into vect will be suddenly the category of all vector bundles over M, not just trivial. And in particular, this will fix this defect that I didn't really explain properly, but imagine you pick a different definition of vect prime S, let's say, is a category of all vector bundles over S, not necessarily just the trivial projection ones, but all of them. Then the inclusion of vect into vect prime that includes a vector space as a corresponding trivial vector bundle, that's an object-wise equivalence of pre-sheaves, but it's not an isomorphism of pre-sheaves. And the formalism we are going to develop next time will also take care of this problem, that you have pre-sheaves of categories that are naturally equivalent should be also considered the same. And our formalism will take care of this problem also. All right, yeah, so we'll talk about simplicial sets and all that stuff. Yeah, so this may be like a point of transition for the class. Previously, we discussed traditional mathematics and one-categorical entities like smooth sets, C-infinity rings, sheaves, and starting from the next lecture, which will last for a while, I guess, we will be discussing homotopy theory, infinity groupoids, how to work with them, how all of this is connected to model categories and other entities from homotopical algebra. So all of that will be explained next time. All right, any more questions? Great, then let me stop sharing my screen. And let me also stop the recording. I guess it already stopped.